Welcome to the podcast on identifying functions. In this podcast, we're going to discuss the meaning of the word function, and we're going to show you how to identify a function in its three basic forms. The first form is the ordered pair form. The second form is the function notation or formula form, and the third form of a function is its graphical form. So let's begin. We'll begin with the definition of a relation. And we say a relation is a set of ordered pairs. Now, ordered pairs differ from regular pairs is that in an ordered pair, like say the ordered pair 3, 5, there is a first number and a second number. The 3 is considered the first number. The 5 is the second number. And in a regular pair, those would just be two numbers, 3 and 5. There would be no first or second number. So if you look down here at F, G, and H, F has 4 ordered pairs, so does G, so does H. Each of those is a set of ordered pairs, so each of those is a relation. Now the question is, are any of these functions? A function is a particular set of ordered pair. A function is a set of ordered pair such that to each first element in the pair there will correspond one and only one second element. So let's take a look at the first relation F. If I look at the first element 2, there is one and only one number 1 that corresponds to 2. If I look at the first number 4, however, there's a first number 4 in this ordered pair that corresponds to second element 2. There's a first number here that corresponds to 5. So here's an example of a first element that corresponds to more than one second element. So this is not a function. Let's take a look at the second one. Again, the 2 corresponds only to the 1. Here there's only one ordered pair with a 4 in it, so the 4 corresponds only to the 2, the -6 only to the -3, and the 0 corresponds only to the 0. So if I pick a first element x, I know for sure what I'm going to get for my second element y. And that makes it a function. Is a function. Let's take a look at the last one. Again, there's only one pair that starts with 2. 2 corresponds to 1. There's only one ordered pair that starts with a 4. So 4 corresponds to 2. Only one starts with a 6. Only one starts with a 0. But you notice there's a repeated second number. 2 in the second ordered pair, 2 in the third ordered pair. Does that keep H from being a function? And the answer to that is no, it does not. The definition says to each first element there corresponds only one second element. It never says in the definition that to each second element there corresponds only one first element. So this also is a function. That is, if I pick an x, I know what y is going to be. If I pick x equals 4, I know y is going to be 2. If I pick x equals -6, I know y is going to be 2. Whereas in the second example, in the first example, if I picked first element 4, I wasn't sure what the second element was. It could be a 2, it could be a 5. That's why that one was not a function. Now let's go to the second form that you might find a function in. You might find a function in its formula or rule form, such as y equals f of x equals 2x plus 3. And this is called the function form or the formula form of a function. Here I've got 4 functions written in their formula form, and the question is, are any of these functions? Well, they're functions if when you pick an x, you know for sure what y is going to be. So let's take a look at the first one. Suppose I pick x is equal to 5. Then y would be the absolute value of 5 minus 3. The absolute value of 5 is 5. So that would be 2. So when I pick an x, I know for sure what y is going to be. This is a function. Now in the second one, I do something very slight. I take the absolute value off the x and I put it onto the y to see if that matters. Again, I select x equals 5. I get this time that the absolute value of y is equal to x minus 3. And of course, if x is 5, x minus 3 is 2. So I have the absolute value of y is 2. And according to the definition of absolute value, that says that y could either be 2 or it could be negative 2, because if I take the absolute value of negative 2, I will also get 2. Well, when I pick x equals 5, I'm not sure what y is. So this is not a function. Now, it's not the absolute value sign that kept it being from a function. It's where the absolute value sign was. When the absolute value was on the x, it was a function. When the absolute value is on a y, it turned out not to be a function. In the next problem, y equals x squared minus 7, again I want to know if I pick an x, am I sure about y? So I pick again x equals 5. And so x squared minus 7 would be 5 squared minus 7. That's 25 minus 7, which is 18. So when I pick x equals 5, I know for sure that I get y equals 18. This is a function. Let's go to the next one. And again, what I've done is taken the square and move it off the x and onto the y. And let's see what happens. Again, I'll let x equal 5 to see if I know for sure what y is. And what I get is y squared equals 5 minus 7. So y squared is negative 2. Well, y squared can't be a negative. When you square a number, it's a positive. So in the case where x equals 5, y is undefined. Now that does not keep this from being a function. It's okay if for a value of x you don't get any value of y. The problem comes in when you pick a value of x and you get more than one value of y. So let's try a different of x. This time I'm going to pick x equals 10. So this time I'll get y squared is 10 minus 7. Y squared is equal to 3. Now we have a way of evaluating that. It's the square root property. And we get y equals positive or negative the square root of 3. And so I don't know when I pick x equals 10 whether I get y equals positive the square root of 3 or whether I get y as negative the square root of 3. So when I pick an x, I'm not sure of y, so this is not a function. So notice when the absolute value went from the x to the y, that second equation, not a function. When that square went from the x to the y, fourth expression, not a function. Now if that had been a cube, there would have been no problem there. It's the square that brought the plus or minus in that made it the problem. So let's move on now to the last way that you might see a function, and that's in its graphical form. Now, a graph is a set of ordered pairs presented pictorially. Each point on this graph is an ordered pair. For example, this point right here is the ordered pair negative 2 because it's 2 to the left, positive 1, I think it says positive 3 here. It's negative 2, positive 1. That's the point that's to the left and 1 up. And so when you see a graph, what you're seeing is a set of ordered pairs, but you're seeing the ordered pairs graphed instead of just written out in its ordered pair form. So when is it a function? Well, let's take a look at this sample graph over here to the left. If I go to the value of x equals negative 2, and I draw a vertical line, I hit that function only at one point. That is, there's only one point on that function that corresponds to x equals negative 2. That's like when we had up here in the ordered pair form, the second function, there was only one pair that corresponded to the number 2, and that was the pair 2, 1, and only one pair that corresponded to 4, one pair that corresponded to 6. So when only one pair corresponds to a value of x, that is a function. So this would tend to indicate that at least from this test it is a function. But let's move over here to x equals 2 and see what happens. Again, I put a vertical line through x equals 2, and this time I hit my graph in 2 spots. I get 2 ordered pairs, 2, 3, and 2, 1. And what that means is if I pick x equals 2, I'm not sure what y is. So this graph is not a function. There can be no confusion. When you pick an x, you have to know what y is. There can only be one value of y that corresponds. So this leads us to something called the vertical line test, and it goes like this. If no matter where you draw a vertical line, you never hit the function more than once, then that is a function. That's called the vertical line test. No matter where I draw a vertical line, I never hit more than once. Let's take a look at these 4 functions, or these 4 graphs over here, to see if any of these are graphs of functions. We test the first one. I draw a vertical line over here. I only hit the graph once. Draw a vertical line over here. I only hit the graph once. The arrowhead means the graph goes on forever in this direction, so you can imagine if I drew one here, I'd only hit it once. This is a function. There is no place where I can hit the graph twice. I go to my second function. I draw a vertical line here, and I hit the graph twice. Here and here. It fails the vertical line test. It is not a function. I go to my third graph. I draw a vertical line over here. I only hit the function once. Draw a vertical line here. Only hit the function once. Draw a vertical line here. Don't hit the function at all. That's okay. You just can't hit it twice. So this is a function. And I go to my last graph and I draw a vertical line here and I hit it once. That's okay. Draw a vertical line here, hit it once. But if I go into this little tiny area right here and draw a vertical line, I hit that graph twice. So corresponding to this value of x, or this value of y, and this value of y. So when I pick an x, I'm not sure what I get for y. It fails the vertical line test. It is not a function. The vertical line test says no matter where you draw a vertical line, you can never hit your graph more than once. If you can, it is not a function. And that completes identifying functions.